The last segment here that we're going to talk about is working with audio, which basically introduces you to some of the terms and processes of audio engineering. And you'll start to see how some of these principles of sound that we've talked about, they really relate to um, the industry of audio professionals. And again, this isn't a science course by any means, but it's good to understand some of the basics of what sound really is and the things we've talked about, like frequency and phase and amplitude and loudness. Um, you'll see how it applies to some of these things, so it's helpful. But first, let's talk about capturing audio. So this is how do we get audio into a form that we can work with it? We talked about how sound is a wave, a sound wave. How do we get that into something we can actually work with? So to convert changes in air pressure into electrical voltages is what we mean by capturing audio. And that sounds like a bunch of gibberish probably, but that's the change of taking audio and making it analog. So we use things such as microphones as a transducer, which basically means it's converting a form of energy. And so analog signal, it's an electrical, I don't know how to say that right. It's a series of electrical voltages. So electrical voltages are analog. Hopefully this will help it make a little bit more sense. So we've got these three different states of sounds that we're going to be talking about and working with. There's acoustic, which is sound waves. So acoustic is just what it sounds like when you're standing in a room talking with somebody. That's simply acoustic sound. Or if somebody's playing an acoustic guitar or a violin or any of these acoustic instruments, if you've heard that term, the state of the sound is staying in the acoustic realm. Now, when we're talking about converting sound, like I was just saying, we're converting acoustic sound to analog sound. So sound waves to electrical voltages. And we don't need to get into the science of how that's happening exactly. We talked briefly about how a transducer is going to convert that. Now, the next step is taking analog and making it digital. So you've probably heard of analog to digital converters, and that's what you need when you're working with audio on a computer. You need to convert that into a digital state that you can work with. And so if you look at here, it's acoustic to analog to digital. And then here it says, and back again. Basically what that means is you can take something, its lifespan. You could be recording an acoustic guitar. So you play the acoustic guitar, there are sound waves that are created. A microphone is set up and it's converted into analog through the series of electrical voltages. That goes through an analog to digital converter, which is some piece of hardware that takes it into your computer, whatever you're going to use, which changes it into digital, which is numerical values, ones and zeros. When I say back again, it means once you're done with those, when you're working with those sounds, it comes back out again to your ears. It's going to be sent back out through cables to speakers, into sound waves, into the air, and into your ears. So it's going from digital back to analog, back to acoustic at that stage. So it goes both ways. Okay, a couple of terms here. Sample rate. Sample rate talks about essentially the quality of a sound. So how many samples per second are there of this audio that you're capturing? And so a telephone or a walkie-talkie, it's about 8,000 of these samples per second, as compared to, an audio CD is 44.1 kilohertz or 44,100 hertz, or a DVD 48, and on as you can see these. And I think this can help. This visual representation shows you the difference. So each of these red dots would represent a sample. So if this is a sound wave, and you're taking little pictures of it here and there, you have less information here, so it's not going to be as high of a quality or as true of a representation as this higher sample rate would be, where there are a lot more samples or little snapshots being taken of the sound. Okay, dynamic range is available range of volume between the loudest and softest audible accounts. So when you talk about dynamics, that simply means the quietest moment to the loudest moment, that that dynamic range is how big that can be. Because signal to noise ratio is the difference in volume between what you want to hear, such as a signal, and what you don't want to hear, noise. So when you're recording, they say you want a good signal to noise ratio. So if you're recording somebody talking, you don't want noise, which could be an air conditioner in the background, traffic in the background, all these kinds of things, just ambient room tone. If you have too much of that, there's not enough signal, which is talking, compared to the noise, maybe in that sense. You want to cut out as much of that as possible. So strong signal to noise ratio. Bit depth. Bit depth can be kind of confusing for some people to understand at times, but let's just explain it in this way, that bit depth is going to allow you, the higher the bit depth is going to allow you a larger dynamic range. And so when you look at things here, the difference between 16-bit and 24-bit, this is how much of a dynamic range the difference is going to be. So when you're working on a feature film or things of that sort, they usually have a higher bit depth because they really need that higher quality for this strong dynamic range. So at one point you can have really quiet conversation or dialogue, and then another moment there may be an explosion, and you need a huge dynamic range to really get the drama and the impact of something like that. Sample rate and bit depth. Here's an analogy that might help as well. So if you're familiar with cameras, this analogy might work. So sample rate is how many pictures you take in a second, whereas bit depth could be considered the number of colors your camera can discern. So the higher of each gives you better quality, but also gives you larger file sizes. So there's a, you can be moderate about those things if you're trying to balance file size. And waveform, we talked about sound waves before. This is a visual representation of what a waveform looks like in a sound editor, such as Pro Tools and things like that. So you see amplitude here, how large that wave is, how loud, and then this is time, of course, so what's happening there. And here actually specifically is Pro Tools, and you can see here's the stereo audio file, so there's a left and a right channel. You can see the sound wave and the amplitude, and then a mono file up here. And this is what we'll be working with here in a second. In another video you'll be looking at. Then the last thing to show here are audio file formats. It's just good to understand these, know what they are. Uncompressed audio file formats are what you're going to want to work with for high quality things, and when you're working in Pro Tools with most of your projects. Wave, AIFF, an Apple format, or SD2, which is a Sound Designer 2 file. Compressed audio file formats definitely have revolutionized a lot of the way people listen to music now, and they have their pros and their cons. The quality isn't as high generally, but there are some good ways. The perception of that can be argued that some people don't notice the difference as much as others may. But anyway, MP3, AAC, WMA, they give you much smaller file sizes, though some of the quality is compromised. And that should do it for this look at working with audio.